The diagram shows a uniform metal bar of mass 20 kilograms and length 2 meters, freely hinged to a vertical wall and held at an angle of 45 degrees as shown by the force P, which acts at 30 degrees to the vertical. We want to find the magnitude of P and the reaction at the hinge. I'm using an enlarged diagram here, as the diagram is going to get quite cluttered. The weight of 20 G acts at the center of the rod because the rod is uniform. If we consider the hinge here, the components of reaction can be dealt with, as in the previous example, by calling them X and Y. We'll call this point here A, and we're going to take moments about this point. In order to take moments about A, it will help to resolve the forces so they're parallel to and perpendicular to the rod. We don't need to do this with X and Y, since these act at A and therefore have no turning effect about A. Let's consider P. We know that this angle is 45 degrees. We can see that because we have alternate angles. This part of the angle must therefore be 15 degrees. This angle is 45 degrees, and we can see that because we have corresponding angles. We can resolve the 20G into components in this direction, 20G sine 45, and a component in this direction along the rod, which will be 20G times the cosine of 45. If we look at P, it will have a component in this direction, which will be P cos 15, and in this direction. So this is a P cos 15, and this will be P sine 15. The components which act along the rod act directly in towards A, and therefore have no turning effect. The only ones that have a turning effect are this component, and the turning effect is 20G sine 45 times the distance from A, and this one will turn us in a clockwise direction. Since we're in equilibrium, it must be equal to this one, P sine 15, multiplied by its distance from A, which is 2. So we have clockwise moments are equal to anti-clockwise moments. The only unknown here is P, so we can rearrange to get P is 20 times G times sine 45 divided by 2 times the sine of 15 degrees. And this is 267.7 newtons, correct to 1 decimal place. We now want to find the reaction at the hinge. We've gone back to the original diagram, as we may want to resolve things in different directions in order to do this. This is something you should bear in mind in doing questions. Don't be frightened to redraw diagrams. Sometimes draw diagrams larger if you know they're going to get cluttered. Since X and Y are horizontal and vertical, it would make sense to resolve P into vertical and horizontal directions. So in this direction, we're going to get P cos 30. Note this is next to the angle. And in this direction, we'll get P times sine 30. Remember, we now know the value of P. Let's look at the horizontal. We have P sine 30 and x, and since we're in equilibrium, these must be equal. Therefore, x is going to be 267.7 and so on, times sine 30, which is 0.5. So x is 133.9 newtons, correct to 4 significant figures. If we look vertically, we must have y and P cos 30, which act upwards, equal to the 20g, which acts downwards. So y is going to be 20 times g, take away P, times the cosine of 30 degrees. So y is minus 35.84 newtons, correct to 4 significant figures. And note the negative here means that y acts in the opposite direction to that shown in the diagram. So to find the reaction, x is 133.9, which is 133.9 to the right. Y is minus 35.84, so it's in the opposite direction, and therefore downwards. We want the third side of this right-angled triangle. We want to find r and theta. We can use Pythagoras' theorem for r, so r will be 133.9 squared plus 35.84 squared, square rooted. And this gives us 139 newtons, correct to 3 significant figures. We also need theta. Theta is going to be the inverse tangent of the opposite 35.84 divided by the adjacent 133.9. And this gives us 15.0 degrees, correct to 3 significant figures.